What specific problem does the proposed method address regarding the creativity of convolutional diffusion models, and how does it build on existing theories in this area?
The proposed method addresses the problem of understanding the source of creativity in convolutional diffusion models, specifically why these models can generate novel outputs rather than merely memorizing training examples. Existing theories often assume that diffusion models learn an ideal score function, which leads to memorization of the training data. However, this contradicts the observed creative capabilities of these models. The paper identifies two key inductive biases, translational equivariance and locality, that prevent convolutional models from learning the ideal score function, thereby enabling them to produce creative outputs. By deriving a boundary-broken equivariant local score, else machine, the authors provide a mechanistically interpretable theory that explains how convolutional diffusion models can generate structured images through locally consistent patch mosaics, effectively combining elements from different training images. This approach not only builds on previous work by highlighting the limitations of the ideal score machine, but also quantitatively predicts individual creative samples, achieving high agreement with outputs from trained models.
How does the proposed method or algorithm work? Illustrate it step by step, focusing on the transition from the forward diffusion process to the reverse flow generated by the else machine.
The proposed method, specifically the equivariant local score, else machine, operates by reversing a forward diffusion process that transforms a data distribution into Gaussian noise. Step 1 involves the forward diffusion process, where the data distribution, pi_0 var phi, is iteratively converted into a sequence of distributions, pi_t var phi, through the addition of Gaussian noise, ultimately reaching an isotropic Gaussian distribution, pi_t var phi. Step 2 is the sampling of noise from this Gaussian distribution, phi_t sim n0i, which serves as the starting point for the reverse flow. In step 3, the else machine estimates the score function, hat s_t phi, using local neighborhoods of the input image, allowing each pixel to flow towards local training image patches from any location, not just its own. This is achieved by calculating a local posterior belief, w_t, var phi vert phi x, for each pixel, which informs the reverse flow direction based on the closest local training patch. Finally, in step 4, the reverse flow is executed, where each pixel's value is adjusted according to the local training patch it is closest to, resulting in the generation of novel images that are locally consistent patch mosaics, thus achieving creativity beyond mere memorization of the training data.
Can you provide a simple illustrative example of how the else machine generates a creative output from Gaussian noise? Walk through the example detailing the local patch mosaic model.
The else machine generates creative outputs from Gaussian noise by employing a local patch mosaic model, which allows it to mix and match local training set patches from various locations. For instance, consider a scenario where the training set consists of two images, an all-black image and an all-white image. When the else machine starts with Gaussian noise, it analyzes local neighborhoods around each pixel. Each pixel's local patch is assigned to either the black or white training patch, based on which is closer in L2 distance. Consequently, the generated output will consist of locally consistent patches where each pixel's value reflects the majority color of its corresponding local training patch, resulting in a new image that is a mosaic of black and white patches. This process exemplifies how the else machine creatively synthesizes novel images by leveraging local consistency and the flexibility of patch selection across the training set.
What are the theoretical advantages of the else machine over the ideal score machine, particularly in terms of novelty and creativity in image generation?
The else equivariant local score machine offers significant theoretical advantages over the ideal score machine by enabling the generation of novel images through a mechanism of patch mosaics. While the ideal score machine is constrained to memorize training data, producing only exact replicas of the training set, the else machine creatively combines local image patches from various locations, allowing for exponential creativity. This is achieved by removing the limitation of locality present in the LS, local score machine, which restricted each pixel's flow to training patches from the same location. The ELSE machine's ability to mix and match local training patches from any location results in locally consistent outputs that are not merely memorized, but are instead innovative compositions of the training data. Consequently, the ELSE machine can generate a vast array of unique images, demonstrating a clear advancement in the understanding of creativity in convolutional diffusion models.
How did the authors validate their proposed method? Describe the experimental setup, datasets used, and the metrics employed to evaluate performance against trained models.
The authors validated their proposed method by comparing the outputs of their boundary-broken equivariant local score ELSE machine with those of two CNN-based architectures, a standard UNet and a ResNet, across three datasets, MNIST, FashionMNIST, and CIFAR10. They conducted experiments by calibrating the locality scale of the ELSE machine to match the trained models, allowing for a direct comparison of outputs generated from the same initial noise samples. The performance was evaluated using the median coefficient of determination, R², as a metric, achieving values of 0.94 for ResNets on MNIST, 0.90 on FashionMNIST, and 0.90 on CIFAR10, while UNets showed median R² values of 0.84 on MNIST, 0.91 on FashionMNIST, and 0.82 on CIFAR10. This quantitative agreement indicates a strong correlation between the ELSE machine's predictions and the actual outputs of the trained models, demonstrating the effectiveness of their theoretical framework. Additionally, the authors provided extensive case-by-case comparisons to illustrate the accuracy of their predictions against the trained models.
What were the key results achieved with the ELSE machine, specifically in terms of its predictive accuracy, compared to trained neural networks on the datasets used?
The ELSE machine demonstrated remarkable predictive accuracy when compared to trained neural networks, specifically UNets and ResNets, across three datasets, MNIST, FashionMNIST, and CIFAR10. The median, R², values achieved were 0.94 for MNIST, 0.91 for FashionMNIST, and 0.90 for CIFAR10 with ResNets, while UNets achieved median, R² values of 0.84 for MNIST, 0.91 for FashionMNIST, and 0.82 for CIFAR10. This level of agreement indicates that the ELSE machine can accurately predict the outputs of these trained models on a case-by-case basis, achieving a high degree of correlation between theory and experiment. Furthermore, the ELSE machine outperformed the ideal score machine, which only memorizes training data, by providing a more nuanced understanding of the creative outputs of diffusion models. Overall, these results highlight the ELSE machine's effectiveness in explaining and predicting the creative capabilities of convolutional diffusion models.